So in this screencast, and indeed in this class today, we're going to talk about, for you Algebra 1 students, graphing quadratics mainly. And on the screen, what I want you to take note of in your binders there, in your folders there, spirals, if you're watching at home too, is what's called the leading coefficient test. And this is a way for us, particularly with quadratic functions, like I've got over here on the left side of the screen in red, this is a way for us to tell which way the parabola is facing, okay? So I've used this terminology before with you guys, talking about concavity. This parabola is what's called concave up when it's pointing upwards and its vertex is at a minimum value. It's the lowest, kind of like a valley. It's the lowest point on there. That's where it's called concave up. You can think of it like a cereal bowl, and the parabola is where you would normally have a bowl oriented to hold soup or cereal or whatever. Concave down is when that bowl would be upside down, if you will. The vertex is a maximum value. This is what we call concave down. And it's where the ends of the parabola are pointing infinitely downward. Now, I've got some weird terminology also written up there in little quotes. I say field goal and then swole patrol. This is a visual reference to what I mean by what this field goal is doing. So you guys that are watching at home, obviously, you can't really see what I'm doing here, but my arms are in the air like somebody has just kicked a field goal that's good, okay? When the parabola is shaped that way, when it's pointing upwards, think, oh, that's a good thing. They just made their field goal. Or the parabola looks like a smiley face. See, smile, that's positive. So that means that the leading coefficient, in other words, the coefficient in front of the quadratic term right here in this context, is positive. So if, like I gave the example earlier, if I said y equals 5x squared, that parabola is going to be concave up, okay, because its leading coefficient is positive. That's a positive thing. And then if it's a negative leading coefficient, then it's going to be, I call it swole patrol. It's like if Alfred has been in the weight room, getting a little too big. You know, he's got his swole patrol working there, you know, the weight room. But swole patrol, or concave down, that's where the ends of the parabola are what? Pointing down. You can think of a frowny face, okay? That's where it's concave down. Now, over on the right side of the screen, I've got a little extension for you guys. This isn't something in the context of Chapter 8, but it's something of interest to us. You know, if we have a degree of a polynomial function that's odd, so like if you have an odd degree, then it's not going to be pointing in the same direction. The end behavior isn't going to be both pointing up or both pointing down. So like if you had a cubic function like I've got drawn out in green here, again, the leading coefficient is the number in front of the term of highest degree. And it tells you about the end behavior of the function. It tells you what is my function kind of pointing towards at the end. And so I like to say it's kind of doing the disco. You know, like if you've ever seen those disco movies from the 70s, right? The disco is pointing up and to the right, down and to the left. That's when the leading coefficient is positive. And then up and to the left, down and to the right when the leading coefficient is negative. For you guys in Algebra 1, I want you to focus more so on the concavity here with parabolas. But as an extension, you can kind of keep in mind any odd degree polynomial function works this way as well. Okay, this is what's called the leading coefficient test. All right. Now, that being said, we can give some examples. Like in a previous class, I've done these types before. Let me give you just a random example of something maybe to a higher power. Okay, so maybe we'll do like negative 6x to the 8th. Like, could you describe the end behavior as that field goal, swole patrol, disco up, or disco down based on the degree and the coefficient? What do you think? Peter? All right, it is indeed going to be a little swole patrol here. Because it's what? It's an even degree. You can think an even degree means that exponent is 8. So that means it's going to be either pointing upwards or pointing downwards. And then we would pick downwards because what? Because the 6 right there is negative. Very good. That's called the leading coefficient test. If it was something like y equals 4x to the 7th, what would that one be doing? Would that be field goal, swole patrol, disco up, or disco down? Yeah, it's going to be disco up because the positive leading coefficient and the odd degree, we know the end behavior of that function is going to be pointing sort of like that. Now, we wouldn't necessarily know what's going on in the middle, But the leading coefficient test isn't about the middle of the function, right? It doesn't tell me, for instance, where this vertex might be. I don't know yet. But what it tells me is hey, the end behavior of this function is known. Your parabola, in other words, is going to be pointing upwards or pointing downwards. That's real plain and simple as far as the leading coefficient test goes. If you look, that's in your text on page 384 in the gray box. You guys that are kind of following along with me in the text, that's what they mean in that gray box on page 384. Now, I've also talked with you, I've used this word about the parabola, I've called a vertex. Who could tell me in just their own words what a vertex is for a parabola? Chase?
Kind of like where the points come down to.
Okay, good. It's where it turns, maybe. It's where the parabola turns from going, maybe like from left to right, if it's going down, 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 and then it stops and it starts going up, 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 right? It changes from decreasing to increasing. That's a very calculus way of describing it, by the way. Or it's where the function changes from being increasing and then all of a sudden goes back and starts decreasing. If you've been on a roller coaster before, that's the fun point, isn't it? That's the point where you're riding, and you're right at the top, and then you start going downhill. That's the fun part. That would be your vertex, where you change from going up to down. What's another way I could describe it? Jack, you asked a question earlier about this. Very good. We call it the minimum or the maximum. Can we write that down in our notes? If the function's concave up, we call this the minimum point. Minimum. Make sure I spell that right. And then we call this the maximum. Okay? My girls like watching, there's a movie called Tangled. Y'all ever seen Tangled? You know that movie? It's a Disney movie about Rapunzel. And there's a horse in that movie. Anybody know the name of that horse? Maximus. Okay, he's this big, strong, awesome horse in that movie. Well, there's also another show that my kids like to watch. And I think it's Sophia the First. Anybody ever heard of Sophia the First? There's a horse, I think, in that show, too. And his name is Minimus. A little play on the words of Maximus and Minimus. And Minimus is a little bit of a, what? A little bit of a smaller horse, perhaps. So anyway, the idea of the maximum is it's the highest point on the parabola. Is there a highest point on a parabola where it's concave up? Is there a highest point there? Mark, you're saying no. Why not? Well, and what does the parabola do? What do these arrows mean? Yeah, it keeps you pick a point that you think is the highest, and boy, I can find one higher. It keeps going higher, keeps going up, 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 up. So the idea of the parabola that's concave down, like I've got over here on the right side, it most definitely does have a highest point. We call that point the maximum value. So the vertex could be described that way as well. Okay, there's a third and perhaps most useful for our context of graphing parabolas, way of describing the vertex, and that is, it's the point of intersection, and I like how some of you guys are taking good notes today. It's the point of intersection between the curve, the parabola itself, and the AOS. What do you think the AOS stands for there, Stephen? I'll give you a hint. Look on 385. In the gray box. Yeah, very good. The axis of symmetry. Okay. So the idea here, fellas. Alex, you here to take your factoring test? What are you doing? I forget. You got a quiz. All right, have a seat. I'll get you made up in just a second. Yeah, you're absolutely right. It's the axis of symmetry. What does the axis of symmetry do? It splits the parabola into two halves that are symmetrical. Describe what Thomas, what does symmetrical mean? Good. Same on both sides. Are our bodies symmetrical? No, most definitely not. Some people have one foot that's bigger than the other. Our heart is just a wee bit over on the left side. We've got, different internal organs that are kind of singletons. You got one of them and it's on the right or it's on the left or whatever. So our bodies are not very symmetrical at all. A parabola is. A parabola is exactly the same on the left side as it is on the right side. All right, give me just one moment. All right, so we've talked about the axis of symmetry. We've talked about the vertex. Actually, let's put those two things together, shall we? We've discussed how that standard form was y equals, what was it again for quadratic? Ax squared plus bx plus c. All right, from the standard form of a quadratic equation, a quadratic function, you could find the vertex. You could totally find the vertex. Here's how this works out. Our vertex has an x coordinate, all right, of the opposite of b over 2a. Let's write that down. And the way that you find the y-coordinate is just by plugging in the particular x-coordinate. All right, we know that from having studied functions so far, that you plug in an x and you get out a y. So the vertex, that minimum value or that maximum value, right, we're going to be able to find it, and I'll give you an example here in just a second, by taking the opposite of whatever b is, the linear coefficient, and dividing it by 2a, so twice the quadratic coefficient or twice the leading coefficient. And that's how you'll find the vertex. Now the axis of symmetry, what type of line is the axis of symmetry? Good, it's vertical, right? So you're right, it would have a slope of, it's undefined, but it's a vertical line. And what did we say a moment ago, kind of in our introductory review, that the equation of a vertical line looks like? It's x equals a constant. What do you think that constant will be? Whoops. It'll be the same as the x-coordinate of our vertex, because by definition our vertex is the point of intersection between the parabola and the axis of symmetry. So you could write down that the equation of your axis of symmetry is the opposite of b over 2a. Now honestly, some of this is blending itself into what you'll learn more in Algebra 2. Right, so like your Algebra 2 teacher would be more inclined to say, Aiden, find for me the equation of the axis of symmetry for this parabola, right? Usually in Algebra 1, they would leave it and they would say, hey, find for me the coordinates of the vertex. Okay, so I'm giving you a little bit of icing on the cake, so to speak, here with this idea of the axis of symmetry. But I think you're well versed enough at finding the equation of a vertical line to tell that, ooh, if I know the vertex, I know the equation of the axis of symmetry. Okay, Grady?
So the equation of the axis of symmetry is the same as that.
Yes. Now let's make sure, what a great point Grady brings up. The axis of symmetry is a line. What is the vertex? It is a point. And those two things are very different. A line has an equation. A line has an equation. Boy, it burns my biscuit. Who's that sleeping back there, by the way? Pick that head up, partner. Get to work. A line has an equation, okay? So a line has an equal sign and things on both sides. What does a point have? Two coordinates. It is an ordered pair. So please don't be an ignorant boob and say, yes, Coach Morgan, the equation of the axis of symmetry is 5. You didn't give me an equation. Or don't say, yes, the vertex of that parabola is x equals 7. You didn't give me a point. Okay, so know what you're being asked. So like if I asked Chase for a vertex, I'm expecting Chase to give me an ordered pair. If I said, hey, give me the equation of the axis of symmetry, I expect to see an equal sign and two things, one on either side. All right, let's get to an example. This is really where the rubber meets the road, so to speak. All right. Now, you guys had, forgive me for forgetting, but what was your assignment that I asked you to do from Coach Perry yesterday? 1 through 30. Excellent. We're going to extend the due date of that, by the way. I'll make it due Monday, so you guys can kind of ruminate over this over the weekend now, especially that we're talking about it in person. But let's look at 30. Somebody had asked about number 30, right, Nick? Let's look at number 30. We got y. This will be a good example. Y equals 6 plus 6x minus 1/3 x squared. First of all, I hate how they wrote this one out. Okay? What do I not like about how they wrote this one out, Grady?
It's not in, it's not numerical, it's not x squared x.
If you didn't hear what Grady said, he said it's not in the right order. They've got this in some kind of funky order. Let's use our commutative property, good, John, to rearrange this. Okay, so y equals negative 1/3 x squared plus 6x plus 6. Are those the same two functions? Yes, Jacob's nodding his head. Yes, they are the same. All I did was just rearrange their terms. This is the proper way to write out a quadratic function. Okay, this is the proper way to express it. This is what's called decreasing exponential order. DEO, decreasing exponential order. What that means is that your terms count down with their exponents. We had degree 2, degree 1, degree 0. This was the quadratic term, ax squared. This was the linear term, bx. And what do we call this term over here? Constant term. Good. That's easy to remember, right? Because it's c, constant. So this is going to help us determine two things. It's going to help us determine the x-coordinate of the vertex and therefore also the equation of the axis of symmetry. All right, so y equals... Ooh, by the way, what's y equals the same thing as saying? Good, boy, very good. I knew that homework assignment would come in handy. Remember, f of x is a different notation. Did Mr. Perry yesterday talk about why that notation came about? How Isaac Newton and a guy named Leibniz, when they were developing calculus? No, he didn't? Okay. Well, the idea of function notation, when they were developing calculus, they developed the notion of calculus. Two different mathematicians on two different, in two different countries developed that branch of mathematics at the same time, independent of one another, and they therefore used different terminologies. So like this idea of y equals was a guy, and I'm going to totally misspell this, Leibniz. And then this notation was used. This is called Lagrange notation, but it was developed by Isaac Newton. And so anyway, these two cats were developing calculus at the same time, and they just happen to use two different notations. They have different uses and different, pros and cons for both of them. So we want to be familiar with both of them. But what is the negative 1/3? What does this negative 1/3 tell me with regards to concavity? What do you think? A little swole patrol action right here. What is this parabola doing then? Use the specific terminology. If you roll up into your 8th grade class and say, "Yes, Mrs. So-and-so, Mrs. Bledsoe, that is, that's swole patrol," she's not going to know what the dump you're talking about. It is what? CCD. Concave down. We already know that this parabola, therefore, is it going to have a maximum or a minimum? It's going to have a maximum. Good. So we're sort of piecing together this notion of what this parabola looks like in our mind. Can you tell me the x-coordinate? You might have to do a little calculation here. What's the x-coordinate of the vertex? The opposite of b, so -6. -6 over 2a. What would 2a be? -2/3. And then you think, oh my goodness, I've got a fraction inside a fraction. Let's zoom in and look at that a little bit better. How do I handle -6 over -2/3? Jacob? Oh yeah, that boy. What do we do? Yeah, flip it and multiply. So 3 over -2. And then all of a sudden the negatives cancel, the 2's cancel, and what do we have? A good old positive 9. And so that's what our x-coordinate will be. See how simple that is? Just sit there and do a little calculation if you can remember the opposite of b over 2a. Now, where do I find the y-coordinate? What do you think, Robert? I don't necessarily know it just by looking at 6. We'll talk about what 6 tells us in just a minute. But I used a phrase up here earlier for the y-coordinate. Plug and chug. What does that mean? We're not going to, oh, brother, we ain't plugging a random number in. What are we going to plug in? We just found it. We're going to plug in 9. And so, like, if you notice how I rewrote this, f of x, and Jack, thank you for your patience. I'll get your question in just a sec. If we called this f of x, what I want to know then is, what is f of 9? Can you guys, while I answer Jack's question, can you plug in 9 and do the arithmetic and figure out what your y value will be for this example?
What is 9 called?
The x-coordinate of the vertex. X over the vertex. You watching at home, pause your video and plug and chug 9 and see what you get out as an output. What's f of 9? This would be reminiscent of our homework from Wednesday night. All right, so hopefully you guys at home have got your answer. Anybody here already done the arithmetic? Grady, what you got?
I don't know the answer. I'm just wondering, still trying to figure out. They put the 6 over -6 over 2/3, but I don't know how you got 2/3.
All right, I think it's going to be 33, by the way. Y'all can double check your work. If you're watching at home, hopefully that's what you got. I rushed through that, though, so I might be wrong. Grady, I want you to mentally focus in on this bit right here. This right here, the opposite of B over 2A. So the question was, where did that 9 come from? We take the opposite of whatever, we take the opposite of whatever that linear coefficient was, and then we divide it by twice whatever the quadratic coefficient is. So for number 30, this little example, we've said, okay, this is my A value, right? And this is my B value. So that's where we were over here saying the opposite of B over 2 times A. The opposite of B over 2A. All right, and then we worked that out right there. Jacob was correct. He said, hey, flip the denominator and multiply, and we wound up getting our 9 as our value there. Campbell? Ooh, good question. No, you don't. I don't even know what this question asked. I just jumped on into it. They said find the vertex and the axis of symmetry. Use the vertex, at least 4 other points to graph. Oh, okay. No, you don't have to do 33 tick marks. And so let me go ahead and, can we agree that, did I do it right at least? Did y'all get 33?
Yes.
Okay. So let's jump into like what the graph actually would look like. I would not recommend making 33 tick marks. 933 is right up here. 933. We're in agreement that it's concave down, right? All right, so somebody earlier, I think it was over on this side, maybe Robert, somebody earlier had kind of cued in on this value right here, our C value. Okay, that's a special value in and of itself. If you were to take f of 0, what would f of 0 be finding? It would be finding C, but why? Well, I mean, like, what is important about f of 0? Like, what is that on the graph? When x equals 0, it's on the... Nope, you had it right the first time. Your hand was going up and down. So what do we call that special point? The y-intercept! Sorry for yelling. Yeah, if I plug in f of 0, these two terms right here go away, and we're just left with C. In your notes, you could jot down that C is the y-intercept. So that special point that Robert was talking about, 6, that's going to be represented on my graph here. All right, way on down here, by the way. Okay. I should probably move my point over just a wee bit. Let's do that. There we go. That looks a little bit better. All right, so this point right here was 0, 6. What did I say that a parabola is with regards to its shape? It starts with an S, ends with symmetrical. Okay, so if you know there's a point over here, 6 units, excuse me, not 6, 9 units. 9 units to the left. Where is there also going to be another point? 9 units to the right. Very good. So it'd be at what? 18, 6, wouldn't it? 18, 6. Grady? Well, actually, so the question was, where did we get f of 0? We didn't actually have to plug in 0. We could just cover up the x terms. I've talked before about, hopefully, about that being called the cover-up principle. So, like, if you were to plug in f of 0, that's the equivalent of saying let x be 0. So negative 1/3 times 0 squared plus 6 times 0. Both of those terms become negligible, and the only term that really matters is that c value. And so that's where we got our 6. So f of 0 means let x be 0. In other words, I want to be on the y-axis. and then 6 is going to be the resulting y-coordinate. And how could I find 2 other points, by the way? Campbell? And so you're almost correct. You're almost correct. What about the y-coordinate 33? So Campbell's question, for those of you that didn't hear, he said, isn't every y-coordinate going to kind of be represented by 2 points on the parabola? And I'm saying almost. What about the vertex? Yeah, so anything below the vertex, you're absolutely right. There will be 2 symmetrical points, one on either side of the axis of symmetry. Right? Yes and no. So like again, the question being asked, like what if we set y equal to 0 and wanted to solve out the equation? So like y equals negative 1/3 x squared plus 6x plus 6. What if we wanted to solve that equation? You're absolutely right. If that one factored, you would set each individual factor equal to 0. You would get x equals one answer or x equals another answer. What would those special points be? We call those roots or zeros, or what's the other synonym that we use? When y equals 0, they're the x-intercepts. So those 2 values, where do you think they probably would be on the graph? Right about there? And where else? Probably right about somewhere in that neighborhood. Right, Campbell? So that's what that we're kind of getting to where we're getting into more chapter 12 stuff at that point. But just for right now, graphing these, and I do need to wrap up my screencast since I'm almost out of time here. Let me say this. I'll put a pin in your question until we get to solving quadratics more so. And let me just say this. What would be another nice point to plug in? We've plugged in x equals 0. We plugged in x equals 9. We use symmetry to figure out the x equals 18. What should I plug in like x equals 100? Should I plug in like x equals negative 37? What would be a smart value to plug in? Something between what? Between 0 and 9, right? Maybe pick something that's a multiple of 3 because we know that you got a 1/3 up there. So could I plug in maybe x equals 3 and see what I get out? Okay, so what would f of 3 yield me, right? Since the problem asked for 5 points, I think. F of 3 would be, let's see here, 3 squared is 9 times negative 1/3 would be negative 3. 3 times 6 would be 18. See, I'm out of time. Plus 6, that's 24, so 21. So we get the point 321. If you'll put it right here, Alex. Thank you. You 8th graders don't go anywhere real quick. 321 would probably be somewhere right about here. If you'll just set it over there on the corner. Thank you, Anthony. And then we would mirror it to be 15, comma 21. Again, because of what's that property with regards to parabolas? It's symmetrical. Ooh, this is an ugly looking parabola.
Now, whenever we do it, you want us to find those 2 points so we can draw the line.
Yeah, they want all 5 points. So one of them needs to be y-intercept, one of them needs to be vertex, and then the others you can find using symmetry and just plug and chug. All right, I got to call it quits for this screencast. Thank you for watching at home, and finish up your homework on page 386 and 387, 1 through 30.